Okay, hi everybody. So just to say, the outline for this afternoon is as on the short a lecture, a bit about configuring the Lustre file system, then a practical MPI-IO performance, and then I'll talk about higher level parallel libraries, and there are some exercises associated with that. But I won't. I'll be back here to answer any questions. But I thought I would just share. Where are we? PowerPoint. Oops. Okay, so I'm going to talk a bit about efficient use of the Lustre file system, just a few general comments, and a bit about how it maps onto MPI-IO, or at least how MPI-IO at least tries to adapt itself to your Lustre settings. Is, again, maybe more what I should say. So we've talked about this, where are the bottlenecks, and we've seen already that a single process can only write at about 700 megabytes a second, which isn't particularly impressive, but we have lots of processes. But if we imagine these on a single node, we saw that writing from a single node topped out at about 12 gigabytes, I think it was. So it's clear that the now it would, if actually, it would be interesting to know. So we know that a process can only write at 700 megabytes a second. We know that for some reason the amount of data you get off a node is limited to about 12 gigabytes per second. It would be nice to know what the actual bandwidth of an OST is. That's quite hard to measure. Well, what you have to do is the bandwidth of OST is in the many gigabytes per second. So if we write from a single process, we can't saturate the OST. All we know is the OST bandwidth is bigger than the bandwidth from a single process. If we write from multiple processes, Lustre assigns the files to multiple OSTs. So that doesn't help. And if you try and saturate all the OSTs, you bring the file system to a grinding halt. What I did do at one point was to you can actually tell Lustre to put all the files on a single OST. So I basically wrote all the files to single OST, and the OST bandwidth seems to be about 15 gigabytes per second, which you can get that, and that does tally with the hardware specs. So kind of, you're like sort of 700 megabytes a second from a process, 12 gigabytes a second from a node, 15 gigabytes a second for each OST, kind of ballpark numbers. So I've said here, caution, IO benchmarking is very difficult and can be non-reproducible. You're sharing lots of things with other users. The other thing is that caching can give very high IO rates. So in fact, writing read benchmarks is actually quite difficult to do, because if you write the data and then read it back in again, it's probably cached locally on the node or somewhere very close to the node. So you get very high IO rates. Or if you read a file multiple times, the second time you read it, it's cached locally. That's why bench.io writes one very big file to basically, swamp the caches. But it can be, benchmarking is always difficult. Performance measurement is always difficult. IO is particularly difficult. You're sharing you're allocated a node exclusively on ARCHER2, but you're sharing all the other resources, the network, and particularly the Lustre file system. Secondly, always ensure benchmarks run for a reasonable time, several seconds, I always say, and repeat them several times. It's like congestion on a road. Typically, what you get is reasonable run, reasonable run, reasonable run, reasonable run, and then you get one which is very, very slow. So yeah, so that you have to do that. So if you get you often get an anomalous result. So we've talked about this before. I said ARCHER2 has 3 separate watch/work file systems. It seems like we now have 4, which I hadn't picked up on. But each of these work file systems has 12 OSTs and 1 MDS. And as I said, that's a compromise between having lots and lots of OSTs, in which case the MDS would become overloaded, because all users on those OSTs would use the same MDS, or lots and lots of MDSs with a small number of OSTs, in which case, although that would balance the load, it would mean that no user could get particularly high bandwidth. So we've gone for 12. We also have the additional file system with the SSDs, and we have access to that. Again, in fact, I have not often seen particularly good performance from that. Not that there's anything wrong with them, it's just that the bottlenecks tend to be further upstream. So, you know, in fact, you tend to be throttled by the bandwidth you can get from a node or the network bandwidth, and not the actual bandwidth of the OST. So on the spinning file system, we have 20 OSTs, each of which has something like 3 or 4 times the potential bandwidth of the spinning disk. So seriously, so there's 256 gigabytes on each node. So if you're writing, you know, like a gigabyte per process, it could be cached in the memory of the node. So when you write a file in Linux, it doesn't write it to disk. It tries to write it to memory. So there's 256 gigabytes on each ARCHER2 node. So so files of order a gigabyte per process could be stored on the node. However, there will be caching elsewhere. If I go back to this diagram here, you know, these OSs, these are large files. These are large servers which have these disks attached to them. These will have caching in them. These will have spare memory. So, you know, these have lots of memory. So when you write, it may not be cached on a node, but it might be cached on the OSS, for example. So, you know, I don't really understand the details, but for small files, you know, they can easily be cached in memory, or cached somewhere. So you're not actually reading and writing to disk. You're actually measuring the performance. Does that answer your question? So you need to write, you know, many gigabytes, several gigabytes per process to ensure that you're not that it is genuinely going to most of it is genuinely going to disk. No, not L1. Sorry. Linux. If you have 16 gigabytes on your laptop and it's a Linux laptop, if you're only using 4 gigabytes, the operating system will grab the other 12. It just grabs the spare memory and uses it for storing disk accesses. When you write a file, it'll just say how much spare memory is on the system. Oh, I don't need to write it to disk. I can stick it in the spare memory. So it's just memory. Yeah, it's a soft side. Yes, so it's the operating system stroke file system which is caching the data, but it's caching it in normal memory, not in as I say, not cache. Yeah. Okay. Sorry, I didn't explain that very well. So if you do serial I/O, if you just do F open, F write, F close, or whatever the Fortran equivalent is that I used in the library, you're not using parallel libraries. So you've got these 2 ways of doing serial I/O are a single file with controller I/O, which is a single writer, or file per process, many independent writers. In both these cases, if you're doing serial I/O, there's little point in striping the file. Okay, why? Well, for a single file, okay, the performance bottlenecks appear to be elsewhere. So that is the same. That's basically saying that for a single file, you know, you're doing. Basically, it doesn't matter. A single OST can easily cope with a single process, right, running at less than a gigabyte per second. There's no point striping the file, okay, because it just doesn't help at all. Okay, so the capacity of this is an order of magnitude more than this, than the bandwidth from a single process. There's no point. So for single file, i.e. a single file with control IO, there's no point in striping. For multiple files, you're already parallel. If you write 100 files, on average, you'll have 8 files per OST, 8, 12 to 96. You're already using all the OSTs. If you stripe all those files, then you're just making life difficult. And isn't that extra bookkeeping and extra work? So if you're using multiple files, more than a few tens, there is no point in striping them because you're already parallel. We're using many disks. Now, I don't like writing multiple serial files, but it does actually eat up all the disk bandwidth. This is why single file is the default, because most people's files are small, little files. You know, most people are editing small files, writing small files. But this ballpark figure, a single process can achieve about 1 gigabyte per second, which is more like 700 megabytes a second in the absence of caching, how you're writing very large files. That's a useful ballpark figure. So the reason why I don't like multiple files, lots and lots of serial files, is the metadata server can become overloaded. Every time you open and close a file requires you to access, you have to say to the metadata server, I'd like to open a file, please. It has to say thanks, right? It has to go and find an OST to put it on, create it, get back to you, say it's there, whatever. And so it's therefore a serial operation. So therefore, if you do 10,000 opens, they're going to be processed one by one because there's only one metadata server on each file system. And secondly, you're sharing it with other users. So if another user is doing the same thing at the same time, it just locks up. And if you're ever on ARCHER2 and you find the work file system locking up, you do ls and nothing happens. It's almost entirely due to the metadata server becoming overloaded. And often that's because somebody is running on a much larger simulation they've done before. They've previously run on 1,000 processes, they've been okay, they suddenly run on 10,000 and it just locks up. So also the equally, so opening and don't do open, seek, close operations on the same file. There are some codes, open, they shall remain nameless, open firm being one of them, where one of the IO modes is every time it writes a tiny amount of data to file, it opens the file, seeks to the right place, writes it, then closes it again. It's like file systems are optimized for doing please write 10 gigabytes of data, right? Not write 8 bytes of data at some random place in some random file. So, you know, really, you know, from a software engineering point of view, making your IO operations small and self-contained, it makes very elegant code, but the performance is utterly appalling. I'm talking hundreds of thousands of times slower than it should be. So tricks, try not to write too many files. A simple trick is, you know, if you're running on 128 nodes on ARCHER2, that means you have 16,000 processes. If every process opens a file of 60,000 files, that's getting to the limit where it's probably not going to be able to cope. So a file per node is better than a file per process. That does require programming. It requires two things. A, you need to identify. Now, why a node here is an important concept. Is a node is a single client of the operating system. So it's of the file system. The file system thinks that these nodes being as a client, which you can process requests from. So there's really not much point in having lots of IO from one node. You might as well throttle it to each client, each node just doing one access at once. To write one file per node would be nice. You're running on 128 nodes, you get 128 files, not 60. Am I getting my numbers wrong? You have to double check that. I'm very terrible. Yes, okay. So you've gone from 16,000 files to 128 files if you run one file per node, which is good. That requires extra programming. You have to identify all the processes that run the same nodes, and I'll tell you how to do that next slide. You then need to gather that data and do a single write. If you want a cheap and cheerful option, you can say, well, I'll still write 16,000 files, but I'll make sure that I only ever have 128 processes writing at once. Ensure only one process writes from each node at the same time. So that's a more cheap and cheerful way of doing it, which doesn't obviously involves changing your code, but it doesn't involve changing your I/O code. It just means sequentializing your I/O calls. If you must have lots of files, consider multiple directories. Every time if you've ever looked, a directory is just a list of files. If you want to open a file in a directory that has 16,000 other files in it, the file system's got to look through this entire listing to try and find it. Splitting, having one directory per node and then having 128 files in each directory is a better thing to do. It decreases the lookup time for files. All of this stuff becomes important when you're trying to run at scale. And I've got a bit of code here which I've used for how do you serialize I/O on each node. So you've got some I/O routine where you do the I/O here. Sorry, I'm just trying to get a pointer. So sorry, I can't remember. Apologies. This not okay. I'm not getting a pointer. I'm just going to have to use this cursor here. Apologies for that. So, how do I serialize I/O on each node? Well, the first thing I have to do is identify those processes. So this is just MPI. I have to identify those processes which share a node. And there is a newish MPI routine called MPI split type. What this does, it splits your communicator down into subcommunicators based on a criterion. And I don't know what the criteria are, but you might, for example, say MPI type GPU. You might have a heterogeneous system where some nodes have CPUs, some have GPUs. You might want to isolate all the processes that have a GPU. But so there are several values allowed for this parameter. What this says is take MPI world and split it up into subcommunicators, which is called node which will turn out to be a communicator for each node, and put all the processes who share memory on the same node into the same communicator. So this says split the communicator up into subsections where each node creates all the processes that are on the same node. And this tells you how to order them within the node. If you specify your rank, you're ordering in the node the same way they're ordered globally. That's not particularly important. But this MPI split type is a useful routine. And an MPI type shared says split it down into subsections based on whether or not we're on the same node or not. Then within the node, which now on ARCHER2 will in general have 128 processes on it, you want to find out your rank and the size. Of course, it won't necessarily all have 128. So what you do now is you have a loop. It's an unusual piece of MPI code where everybody does this loop, okay? But on each iteration, so this loop in general will go from 0 to 127, but on each iteration, only one of the ranks, if my rank within the node, which is a number from 0 to 127 in general, it's a local rank, only unique on a node, not globally unique, unlike your rank in world. You do the I/O and then everybody else waits. So on the first loop, everyone, there's 128 of a node, we're all doing this loop. We all do rank loop equals 0. Is rank loop equals to my node rank? Well, 127 of the processes ranks 1 to 127 are sitting here, and rank 0, and then the next iteration, rank 1, then rank 2 does the I/O. So it just basically is a simple way of serializing the I/O on a node, which cuts your parallelism down by a factor of 1 to 8. But this code will actually be faster than if you didn't have the barrier in, because then you just flood the system and you get contention. So I've seen a situation where someone was running on 65,000 cores, where simply putting this code in increased their I/O by about, well, first of all, they were bringing the system to its knees. So they were told to please desist from running for a little while. But when we put this code in, it made meant that they didn't bring the system to its needs, but also their I/O was quicker because they weren't. It's like a traffic jam, you know. Or congestion. You know, more people trying to get onto a motorway at the same time can actually decrease the bandwidth. You just get congestion. So I thought I'd put that code up. It's a cheap and cheerful way of I mean, there's similar Fortran translation if you're in Fortran, but that's a nice. This is quite a nice. And you would also want this code if you wanted to have a file per rank per node, you would then open a file which was file dot well, you'd have to now, well, you'd want the unique ID, so you'd have to get a unique ID based on your rank, for example. So you might open a you'd have to make sure you open a file denoted by the node ID, which you can also get. But that's just a useful piece of code there. So no, this is what I'm saying is you have a code that you have a program without all this code in, okay? All processes are writing. So every rank is writing. This achieves exactly the same. Every rank in the entire program writes their file, but they do it on a node by node basis. They do it in turn. Yeah. So everybody is, everybody is writing here. At some point, all ranks, all processes execute this loop. Yeah. However, so you'll get exactly the same answer if you're running on 16,000 processes, you'll get 16,000 files. But this makes sure that no more than 128 processes are ever writing at the same time. Sorry, no more than the number of nodes. Apologies. All right, does that make sense? So that's how, yeah, okay. There is a default stripe size which is 1 megabyte. That seems quite small. I mean, we saw for the bench IO we were writing maybe 16 gigabytes. So 1 megabyte is 16,000 stripes. That's way more than you need to saturate the 12 OSTs. You can experiment with larger settings. I have never had this particularly useful. Don't set it too large. If you set it really large, you won't be using all the OSTs. Because if you set it to a gigabyte, for example, then unless your file is 12 gigabytes, you won't be using all the OSTs. But I have not found any benefit in changing this, to be honest. So this is the thing I wanted to. How does parallel IO work? Well, MPI-IO auto configures the Lustre settings. When you do an MPI-IO parallel IO, it auto configures. So what it does is, first of all, it identifies a small number of aggregator processes. We've seen you don't want all the processes to write because that overloads the file system. You don't want one process to write because you don't get good bandwidth. So it identifies a small number of processes, which are called aggregators, which it tries to spread across nodes. Then the subset, let's say there's 16 of them for want of a definite number. These MPI processes then use MPI collectives to aggregate the data to these processes. So they basically pull in all the data that they have to write. They then perform a small number of large write operations because they've aggregated the data together. And that minimizes the overheads of locking and all kinds of things, which I'll talk about later. This is only possible with collective IO calls. If you do MPI file read all, MPI file write all. If you do MPI file read, MPI file write, that just has to be processed there and then. It can't do this aggregation. If you want to know what MPI is doing, if you set this variable MPI-CH MPI-IO stats equals 1, you get statistics at the end, which says things like how many aggregators they were. It says, I did so many writes of so much data. It produces useful IOs, and that's one of the exercises to see what you get there. So what this allows, this allows MPI to do is, for example, it might say, okay, I've got that my file is striped across 4 OSTs, 4 disks, okay? It could identify an aggregator for each disk, for each stripe. It could pull the data together, all the data it needs for that disk, and then it could write it all out. And that means that you've basically got the best of both worlds. You've got parallel IO, that you've got somebody is writing to all the disks at the same time. That gives you good parallelism. But also, you know that only one person is writing to each disk at once. You don't need to do any locking of the file. So this is the kind of things it will do. It will try and identify aggregators, the actual processes that do the IO, and match them to the number of stripes that you're using. Now, by default, Cray MPI uses 1 aggregator per stripe, and that is not actually a very good thing to do. I will go back to my slide from a previous talk, which I don't know if I still have. Was the one? So if I what MPI-IO does, which sounds like a sensible thing to do, but actually isn't as sensible as you'd think, is it does this. It says I've got lots of nodes. If it says I've got 4 exit doors, 4 stripes, what it does is it opens one door on each carriage. It says I will have one aggregator, one process writing per node. This looks like a nice thing to do because there's no congestion. Everyone knows, you get straight out that door and head straight for this exit here, okay? You're matching the number of writers, the number of aggregators to the number of stripes, the number of disks. The problem is, on our previous system, Archer, that was a sensible thing because the I/O from the disks were quite slow. So a single process could saturate a complete OST. What we've seen here is there's more order of magnitude difference. This guy can only write at 700 megabytes per second. This guy can take about 12 gigabytes per second. So the problem with this strategy is, although it's a very elegant strategy and it used to work 5 or 6 years ago, it's no longer balanced because these OSTs are so much faster than they used to be, and the bandwidth coming from a node is so low. So unfortunately, that's not a good thing to do. So we only discovered this. So this took us a while to realize this when we moved from Archer to ARCHER2, that the balance in the I/O had changed quite significantly. So I've lost my place. Apologies. Okay, so by default, Cray MPI uses one aggregator per stripe. That is not really a sensible thing to do anymore. This default could be changed, and you can use. There's a horrible syntax, but here it is. To use 4 times as many aggregators, 4 per node. You can say X for MPI-CH. Cray CB nodes multiplier equals 4. Star means on all files. So this says for all files, use 4 times as many aggregators as you thought about. The problem with that is that we now have multiple aggregators writing. We have more aggregators, more I/O processes than OSTs. We will have multiple aggregators writing to the same OST, and that causes problems with file locking. And so the default locking approach is very inefficient, but there is this locking mode called Cray CB write lock mode equals 2. So this is basically, I don't quite know what it does, but it effectively tells, as I understand it, tells the I/O system that you're going to be doing a lot of collective I/O, MPI file write all, MPI file read all. Therefore, the actual amount of locking will be minimal. Now, I don't quite understand the details of this, what it does at the lowest level, but you can see that there is a problem if you have more aggregators than stripes. You have more than one process writing to each disk, to each OST. Therefore, they may have to do some locking so they don't overwrite each other. This makes that locking a much less of an overhead. So we have in the past seen this give quite significant performance improvements. However, changes in the system software over the past year seem to have maybe made it not so quite as good. So it's worth experimenting with, and it is one of the exercises, but it's maybe not quite as efficient, as beneficial as it used to be. So this is something which I think it was Maureen asked about. And so the other thing you can do is to switch the MPI version. The lowest level network layer under MPI is called OFI, Open Fabrics Interface, can sometimes have poor collective performance. There's a temporary fix which for OFI exports this magic variable. I already put that in there. However, there is also an alternative. So OFI is the Open Fabrics interface, which is an open standard. Because of the configuration, the hardware details of the ARCHER2 system, we can actually use a protocol called UCX developed by Mellanox. It's different, and it seems to be better for collectors with heavy communications loads. So, for example, if people are doing parallel FFTs, which have very heavy all-to-all communications, we've seen that UCX is better than OFI. We've also seen the same with MPI-IO, and I think we saw that already, that this gave a more than 50% improvement, sort of 4 to 7 gigabytes per second on 8 nodes. So that was worth doing, and it's for free. You don't need to recompile, you just need to test it out. Common mistakes that we see in parallel IO: text data files. Okay, I mean, don't write text data files. They're bigger than they need to be. An 8-byte double becomes more than 8 characters, but also the processing, it just, IO is slow. Don't make your life hard. Okay. Multiple accesses to a large number of small files is another problem. We've seen that. Using striping for serial IO. There is no point striping if you're doing file per process or controller IO, because you're either only using one OST or already using them all. The parallel IO mistakes are using a parallel IO library, not striping the file. I've seen people, spend a lot of time putting MPI-IO into their program and then come back and say, my IO is exactly the same as before. Well, that's because you didn't stripe it. And although you can control the striping between 1 and n, where n is 12 on ARCHER2, I have never seen any benefit of anything intermediate value. So I would either not stripe the file or stripe it across all OSTs. The other parallel IO mistake are using non-collective individual IO to a single file. If your program is full of MPI writes and MPI reads, it will go slow. You need to MPI write all, MPI read all. And the final thing is, people sometimes send inquiries and say my IO is slow. It takes 5 minutes. You're like, well, okay. My commute to work takes an hour. Well, if I'm commuting 30 miles, 50 miles from outside of London, that's fine. But if I'm commuting 2 miles within London, it's not fine. You have to quantify your performance in terms of gigabytes per second. Okay, not it took 5 minutes or it took longer than my laptop. Yeah, and I think you should be able to achieve an excess of, well, round about 10 gigabytes per second. We saw that the IO, that the bandwidth from a single process was 700 megabytes per second. You've got 12 OSTs, that gives you about 8 or 9 gigabytes. You should be up in that kind of level. Yeah. If you're down under a gigabyte per second, you're not getting any more than you would get from a single F open, F write, F close on a single process. So 10 gigabytes per second is not really where we'd like to be. The hardware characteristics are probably more at the 100 gigabytes per second. But quantify your performance in terms of how many gigabytes per second am I writing or reading, and if it's significantly under 10, then that's a problem. If it's 10 or more, they're probably doing okay. That doesn't mean we can't improve it some more. So the conclusions for parallel IO to single shared file: use a high-level parallel IO library. We've only seen MPI-IO so far, but I will cover HDF5, NetCDF, and ARCHER2 in the next lecture. Use collective falls. Strike the file across all OSTs with that thing. For serial IO, which is single or multiple files, do not strike the files, and consider writing a file per node. File per process may overlay the MDS, so consider file per node, or possibly, as I said, serializing on a node, just to throttle that total number of files being written at once. That was that. So the exercise now is just until 3 is basically to, I'll just get the, yeah, we do. So the exercise is, we've done MPI-IO performance and saw that we got maybe on 8 nodes, we got 4 or 5 gigabytes per second, or maybe up to almost 8 if we use the different, here's the, yeah, so here they are, yeah. Maybe set MPI-IO such that we'll see what it gets. We can multiply the stripe size. We can try this, and that would be interesting to see those results. And we can try this increasing the number of aggregators per stripe, maybe to 2, 4, or 8, and see what that gets. So that's just that's basically taking the current MPI-IO exercise, which we were getting 4 or maybe at max 7 or 8 gigabytes per second. Sorry, the default session is getting about 4 gigabytes per second on 8 nodes for a fully stacked file. See if we can improve that. We've seen that this improves it already. Maybe this improves it. Maybe this gives you some useful information. And then we'll come back in 20 minutes and I'll give the final lecture at 3 unless there aren't any other questions.